Hi, this lesson is the first in a six-part series learning about probability distributions leading into doing calculations with normal distributions. So the first thing we have to do is understand what probability distributions tell us. Okay, so we know that probabilities tell us about how likely things are to occur, and we've done some work with calculating probabilities so far. A probability distribution is a representation of those probabilities. Sometimes it's in table form, sometimes it's in a graphical form, and we'll see a range of different graphical forms that can show up. So reading directly from the table, I might notice that the probability that a value of 1 occurs is equal to 0.033. The probability that a value of 2 occurs, we would write as p x equals 2 is equal to 0.020. Okay? What will come up is that sometimes we might not be interested just in the probability that x is equal to a value, but that it's equal to a range of values. We might be equal to the probability that we have a value of 3 or more, right? Then we would use the greater than or equal to sign. Okay? To calculate the probability that x is greater than or equal to 3, I'd have to think about all the different categories that is equal to and add them up. So that would be the probability that x is equal to 3, plus the probability that x is equal to 4, plus the probability that x is equal to 5. And if we add those values up, it comes out to 0.947, right? Another thing that we might consider is the probability that x is less than a particular value. Notice I don't have the equal sign here, so this is strictly less than. And so the only value that's less than 2, we'd be looking at the probability that x is equal to 1, right, which comes out to 0.033. Okay. Our tables can be larger or smaller, so now that we've introduced that idea, take a second, pause the video, and try and complete the next 4 questions for the moth. We've got a probability distribution for the average number of female moths out of 14. What's the probability that x is equal to 6, less than or equal to 2, greater than 14, or less than or equal to 14? For part A, you can read directly off the table. For B, we have to add up all categories that are less than or equal to 2. For probability that x is greater than 14, we know is impossible, it's equal to 0, and less than or equal to 14, even without adding them up, we know that they must add up to 0. Add up to 1, sorry. Okay, so both of these first 2 examples that we've looked at are examples of what we call discrete random variables. Discrete random variables are things that can be counted, right? Oftentimes, though, what we're interested in are variables that are continuous, right, that go over a range of values. And we've talked about continuous measurements before and how the more accurate device we use, the more accurate we can measure things with them. Okay, so again, I want to make sure that we're all comfortable with this idea of discrete and continuous variables, and have you pause the video and think about the next 4 examples and consider, are they discrete or are they continuous? Weight is measured, it's continuous. The number of burgers is a count, it's discrete. The amount of time you spend on anything is continuous, it's measured. And the number of eggs laid by a chicken is discrete, again, because it's counted. Okay, excellent. Okay, before we move on, one more example. We have a probability distribution graph for a unfair 6-sided dice here. We want to complete the probability distribution table. We'll use our proper notation, our probability x is equal to a particular value, and fill that out, and then using that table, calculate the probability of rolling a 1 or a 6 with this unfair dice. Okay, so the probabilities are 0.1, 0.2, 0.2, 0.2, 0.2, 0.2, and 0.1 respectively. Again, we can check that the sum of those adds up to 1, and the probability of rolling a 1 or a 6 is 0.2. Okay. So there's different types of discrete distributions that we can commonly encounter. You won't have to be familiar with these terms, but I just want to introduce them. So one type of distribution that we've started generating probabilities for are binomial distributions. These were for when we had groups of people and we were trying to figure out the probability of having 1 in the group or 2 in the group or 3 in the group having a particular attribute, and we used tree diagrams to help us figure out those probabilities. You can notice the particular skewness here. These binomial distributions tend to be left skewed. Okay. Another type of distribution we can have is what's called a geometric distribution, and that we're trying to figure out how long until we get a particular success. If we know that a success only happens a certain percent of the time or with a certain probability. Geometric distributions tend to be right skewed. Okay, and then our third common discrete distribution that we can see are Poisson distributions, where we have an expected number of successes that happen in a time frame. So these could be waiting times at an emergency room, or again, we have maybe how long until an environmental catastrophe occurs or something like that. And so again, these distributions tend to be right skewed. So just for discrete distributions, we can organize the probabilities in tables, we can make histograms, we can make bar charts, okay? But the majority of the rest of these notes and this topic we're going to spend doing continuous probabilities. We're going to be working with something called a normal distribution curve. Whenever we're calculating probabilities related to continuous probabilities, we're going to actually be using probability density functions, and the probability, instead of being given by a value on a particular bar, is going to be given by the area under a curve or under the graph. Okay. So what we have here is an example of a continuous distribution. We have a bus goes by a stop every 12 minutes. So depending on when you show up, there's an equal probability of how long you'll have to wait. Okay, because it's 12 minutes and the total height of the curve is at 12, or 1 divided by 12, which is 0.08333. For question 8, we're asked what's the probability of waiting between 3 and 8 minutes. To write that out, we'd put the probability that x is between 3 and 8, so x is greater than 3 but less than 8, and we'd say that that's equal to, well, we'd have to figure out what that area is. So what we're finding on our graph is the area between 3 and 8. Okay, because in this case it's a nice rectangular region, we can take the width of our rectangle and multiply it by the height to figure out our probability. When we multiply it, that comes out to 0.41665. To be consistent with what we've done earlier in the course, we're going to round that to 4 decimal places, so we'll report that as 0.4167. Okay. Our next question, we're asked, what's the probability that we wait less than 2 minutes? To write that, we could write the probability that x is less than 2, and we'd be finding the area between 0 and 2. This is the same as our probability that x is between 0 and 2. So again, we think about what the width of our rectangle is, we think about what the height of the rectangle is, and we do 2 times 0.0833. Calculating that out in our calculator, it comes out to 0.1666. Okay, so that finishes off our introduction to probability distributions. The next part of notes is going to introduce us to the most famous continuous probability distribution that there is, the standard normal distribution. And and we'll solve some interesting application questions with that. No homework here, just make sure you understand the notation that's introduced and the concept of probability and the difference between continuous and discrete probability distributions. Okay, take care. If you have any questions, don't hesitate to send an email.